A little bit.
Yeah.
It's a bit of like renovations, like paintings, more likely.
Wait, when's this room?
Yeah, we're gonna use this ripple possibly this week, hopefully, because I'm still doing something on there and fixing up the camera there, which is quite hard. Have you been?
I haven't really. I'm just feeling like relaxed.
Yeah, that's good. Yeah, that's what you need for this holiday. And I must say, holiday's over now. Yep.
Yeah.
Okay. Did you get any by any chance? Did you get your results back for the physics?
No, not yet.
Okay, that's
Yeah, my school said they will give out like back at the start.
ooh, that's scary. Yeah. Okay. By the way, you're on live on YouTube now, so as I said, that's only for the people who couldn't come to the classroom.
Yeah, wait, when I first saw the message, I was
Yeah.
confused, but when I saw like the second email,
Yeah.
it made more sense.
Yeah, because someone actually emailed me like, "Oh, so we don't have to come to the class." I mean, no, I'm sorry.
Yeah.
Like, if I made it confused, you still need to come in. Because I need to handling on your like workbooks and stuff, and the homeworks from your holiday, and stuff like that. Okay. It's gonna be a small class today because many of those people are still on holiday, so they're in overseas somewhere. I don't know. Okay, waiting for the print. Hello, Steph. Oh, we're in this room now today. Yes. I might need to go through that after class today because we got to start at class. But here is your workbook, Mod 6. Okay. And I also need to discuss about your assignment for next term. So let's start early and finish early so we can start to write up your reports during the holiday. We can just check it up like the first 2 weeks and hand it in so you don't have to worry about it. Okay? Because it's due week 4, if I remember correctly. It was early term 1. I can't remember exact date. Week 8. Ooh, plenty of time. Okay. So hopefully we can finish the assignment by week 4, which means you have plenty of time to prepare for something else coming. I guess that would be only one assignment for physics for next term, and then
This time is the investigation, next time is the
depth study. So it would more likely, I don't know, maybe an exam again. You never know. Okay, but yes, that's kind of like report writing is the chance that you can boost up your internals. So because many people get above like 90s. Do you know your Orin? Orin, do you know the average for the chemistry assignments?
No.
Okay.
Probably like, if I had to guess, probably like 20, like
Mm.
6 or something.
Out of 30.
Yeah.
Okay, that's pretty high. Okay.
Yeah, because a lot of people, like, I think 8 other people got full marks of that.
Ooh.
Yeah, so
Wow. They marked a really lenient sign. Okay. I know one guy who's joining chemistry tomorrow from your schools. He got 96% as well. So I was assuming. Hmm? This is your task here.
Wait, who is it?
Do you know someone called Tongha?
Oh, yeah, yeah.
Yeah.
Like, yeah.
Yeah. He's joining us. So he
Okay.
he dropped it from like the year before because of
Yeah.
and then he came back. Yeah, it's good. So it's a fresh start, good start. I need to start it now. Any news from Daniel? He dropped out. Dropped out.
I don't know, he went like somewhere else. He said he's going to like Zhang's.
Oh, good luck.
Yeah.
Zhang's is like, okay, never mind. All right, today we are going to start about module 6. So before we start on module 6, we need to introduce a little bit more about some charges and other stuff. I know many of you, actually you too, didn't have E11 class with me, so you probably don't know like what is going on once we start module 6. So we're going to start with the basics of the electricity. Okay, so give you some understanding about electricity because whole module 6 is about electromagnetism. You need to understand about what the electricity is. So, have you ever heard about something called a charge? Steph, have you heard about the charge? Okay, when do we use? I mean, like we use. It's good that like both of you doing chemistry. We use quite a bit of a charge in chemistry. That we believe that electrons carry some negative charge, protons carry some positive charge, so that is making some kind of atomic structures. There's a positive inside and negative kind of hanging around. Okay, so the one simple rules about charge is a universal, or both for chemistry and physics. Charge is always be the opposite attracts. Okay, it's very simple. It's opposite attracts, and the same side, the same charge, repel. What that means is when we have plus and negative, positive and negative, they will be attracted to each other, as we learned from the chemistry somewhere in like in physics too. But if we have plus and plus, they will repel to each others like this. Okay, it's very simple terms. Okay, there's one rule that you need to remember that before we move on to the module 6. Second, when we talk about charges, we are talking about very specific particles that carrying the charges there. Those particles carrying charge or charges, there are a few. One is obviously we know the electron that carries a charge. Okay, electron is like a small little particle that carries the negatively charged, so it's a negatively charged. Does anyone remember the charge that carried by each of the electrons? Okay, if you don't, it's called the QE minus or QE. That's known as minus 1.602 times 10 to minus 14 coulomb. Okay, C is known as the unit of the charge. That means that each of the electron carries this much of the charges. In other words, we can count that. This is something that's very important in the module 8 as well too. If we have a few, let's say 10 of the electrons, the total net charge of that would be times 10 of that. Does it make sense? Okay. Now, we also know there's a protons, which is positively charged as well too. Again, using a little bit of understanding in chemistry, as we believe that electron carries a -1 charge, -1, proton carries +1. In physics, we trust that proton and electron carries the exactly same amount of the charges, but simply they're opposite, which means it'll be plus 1.602 times 10 to minus 14 coulomb like that. Okay, so in physics, we are using very specific numbers to figure out the charges in terms of like a quantitative, the total amount of charge. Okay, we also have something known as alpha particle. Okay, Orin, do you remember what the alpha particle is? When we say, hi, about alpha decay or alpha particle.
Is it like it loses like
protons and it's been a while, and we did that in year 11 in chemistry, by the way. Steph? Helium nucleus. Now, the question is, what is inside of the helium nucleus then? 2 protons, 2 protons. Sorry, we write it as 4-2 helium like that. Okay, which means if you remember that the neutrons do not have any of the charges. When you have 2 protons, the net charge of that, the Q of the alpha would be 2 times of the proton's charge. Why? Because the helium nucleus carries the 2 protons inside, which means this would be 2 times 1.6 or 2 times 10 to minus 14 coulomb. So basically 3.0, 3.2 or 4 times 10 to minus 14 coulomb. Does it make sense? Okay. Now, the reason why I'm bringing up the alpha particle here is, again, is yes, you're going to learn about alpha, beta, and the gamma again in your module 8. If you have some basics of the understanding and the basics of the chemistry, it's actually helping you quite a lot to understand what is going on. Second thing is, I want you to remember about the difference between protons and alpha particles. Yes, both of them carry the positive charge, but one is carrying the twice of the charge that one inside in the protons. That means alpha particle or the helium nucleus carries the having the charge of twice of the protons, and the mass-wise, do you remember the mass of the proton and mass of neutrons are quite similar, or they're almost the same? Okay, this is 4 times heavier. I would say this is 4 times heavier. Also be 2 times of the charge of the proton. This is something they're loved by the examiner. They love to show that, oh, we have alpha particles and compare that with the movement of the protons or the electrons too. Electron's mass is, if you remember that again, is much lighter than the proton. It's over 1 pound. It's 1 over 2,000. So we're going to go through that again later. What that mean in this time? All right. Now, Then why do we care about these charges? Because charges, or the particle carrying the charges, is everything about, it's all about the electricity. So let's talk about electricity then. When we simply call it electricity, there's two things we can describe the electricity. One is about the voltage. Okay, yes, we describe the electricity as like a high voltage or not too. So for example, we have of the 220 volts, okay, or 240 volts, that depends, 110 volts. So what does that mean by like having different voltages? Okay, the simplest way to think about what the voltage is you may think that voltage as like the quality of the electricity. In other words, the speed of the electrons in a circuit. Why do we concern about the speed? Because when something is moving at the highest speed, that means that it's also related to the greater, the kinetic energy of the electrons. So it simply means 110 volts compared to 220 volts. Okay, this means that 220 volts has twice faster speed the electrons than the 110 voltage. Okay, now if you remember that the energy content, the concept we learned in the year 11, kinetic energy, can we also say the kinetic energy also related to some sort of the potential energy? According to the conservation of the energy, if we have electron that stores some potential energy, say 10 joules, okay, it now has some potential energy. When it starts to move, it converts into kinetic energy of the 10 joules again. This is known as what? The conservation of the energy. So in other words, we can also talk that kinetic energy electron is equivalent to the stored energy, which is a potential energy of the electron as well too. Simply means greater the potential energy stored by the inside of the electron means that the greater kinetic energy can be converted into. Therefore, they can move faster. You okay, Steph? Well, depends on the situation now. When the circuit is connected, when we're having carrying the battery here, okay, just let's say AAA battery. Before it gets connected to the circuit here, it stores some of the energies because it's not, the electrons inside there is not really moving yet. Now, once it's connected to a circuit here, means that the electrons have started moving from the negative terminal to the positive terminal in this way. Which means when in the closed circuit, yes, we get the kinetic energy because the electrons are able to move in the circuit. Does it make sense? Oh, that means that there's no potential energy anymore because all that potential energy is converted into the kinetic energy. It's basically the same as I'm holding my pen on the top here. This stores a potential energy, which is called the gravitational potential energy. But if I drop it, when I drop it, now it converted into the kinetic energy. Okay, does it make sense? Okay, so I'm using a bit of like an energy content we learned as well. So this is why sometimes the voltage is described as potential difference. That's simply known as a voltage. Why? Because let's draw the battery again too. We have a positive terminal. There's a positive and negative terminals there. Inside the semi-permeable membrane, we have a lot of electrons are gathered in here. Okay, what about this side here? This is where we no electrons whatsoever because the reason why the battery is negative is because we have a lot of the electrons that are gathered. Does it make sense? Okay, means that we have a certain potential energy stored in that electron, just like I'm holding my pen on the top. And if you compare the potential energy between this one to the positive charge over there, it makes differences too. In other words, I can tell, it has a charges and we have a really strong positive there. When I connect these two, okay, because according to the charge number one rule, the opposite attracts. Okay, these electrons will be able to move to this direction. Now they cannot go across that because we have some kind of barrier or semi-permeable, the membrane over there. So electrons will be moved towards the positively charged terminal. This is how electricity is converted. Electricity is kind of produced. Does it make sense? Okay. The second term we use to describe the current electricity is known as the current. Now, current is slightly different to the voltage. I know many students get confused about voltage and currents in the different times. Current is simply, you can just understand it as a quantity of the electrons. What does it mean by the quantity? It simply means the number of the electrons that are inside of the battery. Okay, if say we have a 10 amp compared to 100 amps. That means that in 100 amps, it has a 10 times greater amount of the electrons than the 10 ampere. Does it make sense? Okay, this is something that you have to understand. And the current has the unit of the amp, amp, okay, as a symbol of the I. The one thing you have to understand in here, I used to describe the current as like, you can imagine about a narrow channel, a river. If there's a lot of fish, let's say salmon, whatsoever, okay? If they're moving into the one direction, like this, okay? I want you to imagine, you need to use a bit of imagination here. When the fishes need to swim forward, what they do is, you're kind of pushing their water backwards. Okay, if you swim, if you have ever swum, you need to grab the water, pull backwards so that you can move forward. Does it make sense? Okay, so if this is a direction of the fish going to this direction here, the direction of the water, because we have lots of the fishes inside the narrow channel of the river, okay, means that all the fish is moving forward, they're kind of pushing the water backwards, makes the direction of the some kind of movement of the current or the water in this case. Okay, what I need to do here is I just need to simply change the fish and the water into the electron. Exact same things happen inside of the copper wire. What that meant is when the charged particle electron is moving forward, okay, that's electrons kind of pushing the currents backwards, producing the energy backwards. Or if this is too hard to understand, just simply remember one term, that the direction of the current is opposite to the direction of the electrons. Yes. A is the unit, I is a symbol. Like force has the symbol F as a unit of the Newton. Okay, all right. Voltage is quite confusing. Voltage has symbol of the V, a unit of the V. This is something that makes you confused. I know that too. Okay, but current has unit of symbol of the I, the unit of the A, ampere. Does it make sense? Okay, this is up to what you learned in chapter 1 or 2. So let's have a look at the this is from year 11 notes. I'm printing it. The print is not working. Whatever. Okay. Can you see the board here, the pictures? Now, this is what I mean by the charged particle inside of the electric circuit. Now, when the positively charged particle is moving from one direction to another, it will now have some sort of the kinetic energy because it's moved. Okay. Now, talking about kinetic energy, then, according to the conservation of the energy stored inside in the initial position of the Q is now lost as it's converted into the kinetic energy. So when we say the voltage in physics, we describe that as voltage is something about change in the potential energy divided by the charge carried by each of the charge. that charge can be any of those charges here. Okay, very specific number. In other words, if you want to find that, the kinetic energy, I hope you remember that, change in the potential energy. Do you remember this from the gravitational potential energy here? It's 100 joules stored, 0. Okay, the delta U would be 100 or minus 100. But what about change in kinetic energy? If something dropped from this certain height to the bottom, okay, initially the pan stored 100 joules. When it dropped, all the energy, potential energy, get converted into kinetic energy. So change in kinetic energy also be 100 joules as well too. Do you remember this contents? Okay, which means delta U is equal to delta K. So can you apply the same rules over here? This means delta K is equal to Q as well. Or this is sometimes known as work done on the Q as well too. Okay, yes. Work means that amount of force carried in the certain distance. That's bounded by F times S on Q. It's like I lifted up something. I did some work because I did work against the gravity. I put some force to move that to a certain position too. Okay, the easiest way to understand the work is you're going to the gym and you're working out. Basically, you're lifting up something. Then you're doing work against a certain gravity. That means you did a certain amount of the work and converted it into your energy too. Okay, now the reason why I'm bringing up this here is I can convert that into here. This gives us the voltage is same as K on Q, or delta K on Q. In other words, delta K is same as the Q times the V, where the V is the voltage. Remember that voltage is describing the how fast or the kinetic energy. So greater the voltage means that greater kinetic energy. In terms of, and they have a directly proportional relationship too. There is some questions giving you that in the scientific skills, asking you to plot the data between the voltage, the kinetic energy of the electrons, and find the relationship of that too. Yes, you can have that as well. And just give you a clue and a hint that this is possible. Now, all right, what is a delta K? What's a K equals to? What's a kinetic energy formula? Very good. We half mv squared. Q times V. Which means that if we know the voltage of something, voltage of the circuit, we are able to find the velocity or the speed of that electrons inside of the circuit as well too. This is something that you will never learn in schools because we assume that you learned it in year 11 or year 10. If you didn't, this is a chance. Okay, this is something that really popular comes out in the school exam and the HSC as well too. They're giving you the voltage and asking you the head, what's the velocity of it? Therefore, find some motion of that. Okay, so let's have a look at some questions related to this. I'll try to print this one. I could probably give that. But let's see the example. When a charge of the 2.5 times 10 to the minus 4 coulomb moves between the 2 points in the electric field, the electric potential energy of the charge changes by 5 times 10 to the minus 2 joules. A, calculate the potential difference between 2 points. Okay, now, whenever a question is asking a potential difference, as I said, okay, this simply means you have to interpret that this means a voltage. Why am I saying the voltage? Because we learned that as voltage is about quality, how fast, or the change in the different the potential energy between two. Okay, so even though the question didn't specify like a voltage in the questions, you have to kind of get that point that potential difference is actually equivalent to the voltage. Does it make sense? Okay, so don't get tricked by that. So what we know, let's write it down. What we have, we're given Q is 2.5 volt times 10 to the power minus 4 coulomb. Change in the U, which is the electric potential energy of charge changes, is given as that. So 5.00 times 10 to the minus 2 joules like this. If you know the formula, if you understand the relationship between the potential energy or change in potential energy to the voltage, you straight go to V is equals to, voltage is equals to delta U on Q straight away. It might be on the formula sheet, but I recommend you to memorize it. Just same as F equals to MA. No, it is what it is, as this. Or you may say delta K on the Q. You may need to show that according to the conservation of the energy, but you don't have to explain it. So, or we can get the voltage then, 5.00 times 10 to the power minus 2 divided by Q value, 2.5 volt times 10 to the power minus 4, like this. Okay, put it in your calculator. Then 5 times 10 to the power minus 2 divided by 2.5 and 10 to the power minus 4. You get 200 volts. It's carried by these charges then. Does it make sense? Okay. Now, it's very important to understand because the HSC question nowadays, they kind of try to trick you by giving some energy related to the voltage a lot. Okay. And it is very important that you need to picture or to imagine that electricity or voltage and current is all about the moving charges. Yes. So I'm talking more about mechanics again. Energy, speed, possibly acceleration, and the some other kinetic energy as well too. That's for A. B, calculate the change in potential energy if a charge of the 7.6 times 10 to the minus 2 coulomb were moved between the 2 points. So we now have a new charge that is 7.60 times 10 to the power minus 2 coulomb. Okay, that is moved inside of this voltage. Okay, I give you about 30 or 1 minute to think about question B. And try to imagine that what is going on in here. And can you also find that the velocity or the speed of the charge inside of that voltage? Okay, so things you have to remember, you have to see from the two questionnaires. One, question A gives you a charge that 2.5 times 10 to the power minus 4 coulomb. Okay, compare that to this new charge that is 7.6 times 10 to the minus 2. This is much bigger. It carries a huge amount of charge. I'm not talking about the mass of it. It carries this much of the charges too. So I hope you remember that the first rule of the electricity or the charges, the opposite attracts. That means that it will be, this charge is a positive charge, will be attracted to the negative side much faster and a greater amount of the energy, more likely. Does it make sense? Okay. Can you imagine that? This is something that's very important to picture that. So now once you understand the picture of this, you can just simply apply the formula. That is, the V is equals to delta U times Q. That means delta U can be found by QV. Okay, that is 7.60 times 10 to the power minus 2 times the voltage, which is given as 200. As you do, put it in your calculator, times 200, you'd get 15.2 joules. This is the amount of the energy that is carried by or stored inside of the charge, or difference between two charges, 2 points. Does it make sense? Okay. If this is the same as the kinetic energy as well too. So if I give you like, the mass of the charge, say, I use actual mass of the electron, say if the mass is given as 9.109 times 10 to the power minus 31 kg like this, if that's given. It's not given on the question here, I'm just giving you the mass here. That means you are able to find that using the half mv squared to find the velocity of that charged particle inside of the circuit or inside of that voltage. So what we do, the velocity, small v, remember that the v, small v and the big V is they're different. The capital V stands for the voltage, small v stands for the velocity or the speed. So don't use that. Small v is equals to 2 times k divided by m and square root of that, which is 2 times, given that 15.2, divided by the mass, 9.109, times 10 to the minus 31, and square root of this. Okay, so 2 times 10 to 15.2 divided by 9.109 and divided by minus 31 and square root of that, you'd get 5.78 times 10 to the power 15 meter per second. This is how fast the charged particle is moving inside the circuit. Does it make sense? Okay, so again, try to picture that as charged particle as like the electricity as like a one set of the mechanics. Okay, this is a pre-assumed knowledge you need to have to understand, to go through the module 6 then. Okay, the second thing. Do you remember that in the magnetism, when there is the current carrying wire, I, again, I stands for the current, that means that electrons are moving into the opposite direction like this. Okay, I write it here. The direction of the I is opposite to the direction of the electrons. Does it make sense? Okay. Now, do you remember that you learned that in year 11 a little bit, that when there is an I, it produces something called the induced magnetic field. Does anyone remember that? No? If you don't, okay, this point, you do not need to understand. Don't try to understand the point, okay? Just try to memorize that as, when there is I, when there is a current, it produces something induced, B, which is the magnetic field. Induced means it's kind of help, it's kind of pushing. It's kind of, before we have an I, there's no B field, but there's no magnetic field. Induced means helping or like kind of causing that B field to be produced. Okay, it simply means when there's an I, there will be B. Okay, so that's a simple rule that you just need to remember. Try to not to understand, because you will not be able to understand unless you're studying some quantum physics later on. This is all related to the spinning of the electrons. I'm not going to go through that. If you are interested, you can study that in university. Okay, but what you need to consider from here is when there's I, there's a B, and if you have seen that, I actually showed you in one of the pictures that in your workbook, that shows you that something like this. I just use part of that. Page 11, it shows that what it means here. When there is I, it produces the magnetic fields according to the right-hand grip rule. Okay, has anyone learned that? Yeah. Yes, okay. Yes, just simply remember that. When there's I, there is induced B field, and we can find the direction of the B field by using right-hand grip rule. There will be lots of the right-hand rules, by the way. So I will introduce some right and maybe some left-hand rules. Okay, the left-hand rules, you will never learn that in schools anymore. We used to do that in many years, but they're still effective. Okay, I'll give you some point of that. Right-hand grip rule means that you simply put your thumbs as like a direction of the current, put it on your eye, goes like this. Means that your rest of fingers are indicating the direction of the magnetic field, which means it will produce the magnetic field in this direction here, going in and out of the page like this. Okay, and as you get close to the eye, it's very simple. It gets close to the eye, the magnetic field gets greater. How do we know it? Because when we place something in here, compared to this position to this position over here, that will have a greater attraction towards the B field. Okay, very simple. Just try to not to understand. Try just to see that, oh yeah, try to accept it. that when there's an I, there's a B. Make sense? Okay. And when you get close to the I, it will produce the greater magnetic field strength. So another way we can show the direction of the magnetic field is we can show that as it's coming into the page, goes like this. Remember the X stands for the going into the page. Coming out of the page is a dot like this. Okay, so you will see quite a lot of the symbols that X and dot. X means that going into the page. That means out of the page. All right, so this is the basics that you need to understand the module 6 from now. I will go through that in basics again and again until you really fully understand some of the points, okay? And I will probably emphasize quite a lot of those again over the time. So let's start the module 6 finally. Page 3, please. So let's talk about some electric field. You probably have done that in year 11 again, so it's good revision. But if not, it doesn't really matter. Now, in module 5, we learned about different type of field, which is called a gravitational field. You remember the gravitational field? That we have the planet or the stars. Okay, let's say this is a planet or a star. There will be some attraction force all around the stars, so that we can show all the type of forces going into stars. That's what I mean. In the stars, receiving this type of the gravitational force. Now, when we set a field, it means that the area or the region that receives that amount of the forces too. So as the stars are uniformly producing the gravitational force around, we call that the whole region of the stars will be in the gravitational field. Does it make sense? Okay. So field, simply remember the field, whenever we call the field, is the basically forces in a certain area. In an area there. So we can describe that as this is an area, receives some of the forces going in there like too. We describe this as a field that receives a certain amount of the forces too. Okay, just like we described the gravitational field in module 5, we can use the same content, same definition to explain the electric field as well too. Okay, now what is electric field? Basically, to produce the electric field, we need to have something in the positively charged plate and also have a negatively charged plate. The simplest method to make this is I connect it to the DC battery. And remember that the longer the line means the positive terminals, shorter means negative terminal. Does it make sense? Means that this is not really connected. Remember, this is not in a circuit. Okay, so what that means is this plate, the metal plate on the top is positively charged. Metal plate on the bottom will be negatively charged here like this too. So, but if that distance is kind of close enough, if there's no resistance whatsoever, we will expect to see some electrons are jumping from this direction to another direction like this. Okay, it's kind of producing that because we have some unseen, invisible forces going in here. The direction of the forces generated inside there would be going into this direction. I call this as electric force. During the force diagram, it will go like this. Okay, now I want you to remember that what does mean by the force. Getting a force in module 1 and 2, maybe in the module 5. Yes, force is known to be the ma, according to Newton's second law. Yes. Green is the direction of the electrons moving. Okay, and it's kind of the same as the current there too. Like as the electrons moving from one negative to positive, it produces the opposite direction forces, or the current in this case. Okay, because current moves from the positive and negative terminals. Let's write it down here. Direction of the current is I is from positive to the negative. Okay, so F equals to ma means that, yes, it means that it will get some acceleration. So let's have a think about the situation where we are placing some particles inside the field. So I'm going to draw the bigger electric field. I need a different color. Here we go. All right, we have something that bigger field. That's a positively charged. There's a negatively charged here like this. Okay, don't worry about the batteries that I drew here. Now, when I placed the electron, so assume that like I picked the electrons, put it into the circuit artificially. Okay, put it into the field. Now, all right, what do you expect for this electron inside of this field? It will attract to the positive because we learned that the prime rule, opposites attract. It will move towards to the positively charged plate. Now, can you describe that motion of that electrons? What would be the motion like? So starting from, I just dropped the electron on the negative charge plate. I dropped it. Can you describe the motion then? You go up, it's good moves. That's a direction. That's a direction. When I describe the motion, means I want you to like describe more about the quantity or like some change in velocity. What do you expect? It started from nothing, like it wasn't moving. It wasn't moving at all. As it's gravitated towards to the positive charge plate, it's getting faster. It's getting faster. Okay, it's not moving in a uniform speed. It's slowly getting started and getting faster and faster and faster. And now, what does it mean by getting faster? Getting faster means that there is a change in velocity. Yeah? What does it mean, change in velocity? We learned that in Module 5, Module 2, Module 1, mechanics again, means that there is an acceleration inside of the field. Does it make sense? Okay, so this is something that's very important. You need to imagine that there's moving in the charges in the mechanics. What about this step? I have something in the positive charge over here. What do you expect for this? You get repelled. Very good. You get repelled by the positive, moves towards to that direction there too. As it's moving towards the negatively charged plate, it's getting faster and faster. Isn't that very similar to I'm dropping a pen from this distance to there? Because we are in the world of the receiving the uniform acceleration, okay, which is called a gravitational acceleration. Does it make sense? Okay, so I give a very simple and interesting fact in here. What about I shoot our positively charged particles with a certain velocity in this direction there. What do you expect? Yeah, it will. It was moving forward and now it's making this motion. What is this motion? This is called the projectile. Yes. So you may get the projectile motion again in related to here. But do we concern about the acceleration due to gravity? We do not, because the mass of the particle, mass of the charge, we can't really see the particles, we can't really see the electrons. They are negligible. So there must be something else. There's something like some other like forces and acceleration applied in the electric field too. Okay, now you see the reason why I emphasize quite a lot of Module 5 and 6. Module 5 contents in Module 6. This is some question that loved by the examiner too, because we love to mix in Module 5 and 6. Okay, but things very simple. If you understand that as, oh, electric field is all about the moving charges, okay, then opposite attracts. That means the negative charge, the particle will be moved towards the positive charge particle move towards the negative plate. Okay, what if I have something in the middle? I drop the particle in the middle here. What happens to this? it will still move towards to the negative charge plate. But the motion will be different too. I'm dropping the two pens at different height. Very simple as that too. So the final speed of that would be obviously different. Does it make sense? Okay. This is the first thing that you need to understand in electric field. Now, the way we can find the force due to the electric field, yes, you may use F equals to the ma. I don't mind to say that. But if the question is only giving you some other values, if you don't have the acceleration, the mass, you can't find the force applied in here. So instead, we're using this. The F, the force in the E field experienced by a charged particle is calculated by Fe equals to Q times the E. Well, the Q is the charge of the particle. E stands for the electric field strength. And how to find the electric field strength? Remember that this is talking more about the energies again too. This is found by the voltage on the distance, or like the D as in like this is D, the height distance between two plates. Okay, why is that? Because if they carry a certain voltage, remember this, V is about change in potential energy carried by the charges. So greater the voltage means that it will make a faster movement. The faster movement means that there will be greater acceleration applied as well too. So everything's kind of applied, everything kind of linked together in this way. So let's have a look at some questions related to here. Page 4, please. In class exercise 1.1. Calculate the magnitude of the acceleration experienced by the electron traveling in uniform electric fields of the 3.1 times 10 to the power minus 5 newtons per coulomb. That's a unit for the electric field strength, E. Okay, so let's write it down, all the relevant information that we have. One, we have QE that's given as minus 1.602 times 10 to the power minus 19 coulomb. Oh, sorry, that's my 19. And mass of the electron is given as 9.109 times 10 to the power minus 31 kg. Okay, now question is asking you to find the magnitude of the acceleration. That means we are able to find that Q, F equals to, I forgot to write this one down. Let's write this. E, electric field strength is given as 3.1 times 10 to the power minus 5 newtons per coulomb. Then we can find the force by Q times C. That is simply minus 1.602 times 10 to the power minus 19. That times that. E field 3.1 times 10 to the power minus 5. So 1.602 times 10 to the power minus 19. That times 3.1 times 10 to the power minus 5. You're to get 4.9662 times 10 to the power 24 Newton. This is the amount of force carried by the charged particle electron inside that given E field. This is what? Same as ma. According to Newton's second law again, so acceleration of the electron can be found by F on m, that is 4.9662 times 10 to the power minus 24, divided by mass 9.109 times 10 to the power 31. So that divided by 9.109 and 10 to the minus 31, you would get 5.45 times 10 to the power 6 meter per second squared like this. This is the acceleration. Okay, so compared to the gravity acceleration due to gravity, this is a huge amount of acceleration, by the way. Means that charged particle or electrons inside the E field will experience change in the velocity quite a lot. Now, could you try for the same type of question at 1.2? You got negative. Okay. For the values here, yes, you would get some negative forces here. Okay. So considering the negative, positive, and negative in the physics, it simply means the direction. It means that. This means the negative value means that moving opposite to the E field. Does it make sense? Okay, so it means if that positive and negative, as the field line goes from positive to negative here like this, okay, electrons will be moving from the negative to the positive, which is moving the opposite of the direction of the E field. Because we're giving the E field direction as something known as positive.
Yeah, so the value of E is like the direction.
Value of E is the like positive and negative would actually indicate the direction of the movement. We take that as E is moving from positive to negative. Having the negative force means that it's moving opposite to the E field. Does it make sense? Okay. All right. Try for 1.2 then, please. Acceleration can be negative too, so but you need to indicate that. Oh, actually, I need to write it in direction too. 5.45 times 10 to minus 6 to from the negative to positive. Because we have a negative acceleration value, which means it's moving against the direction. If this is negative, this is actually negative because we use a negative value here. I'll write it down here if that does confuse you. Does it? Yep, means that it will have a magnitude of the 5.45 times 10 to the power 6. Yeah, same direction. Sorry, the opposite direction from negative to the opposite direction. Is negative to positive, because simply remember that, Steph. For the current and electric field, it's always moving from positive to negative. Okay, means that by having negative means it's moving opposite, which means from negative to the positive. Or simply think that as you're given an electron, which has a negative charge. So obviously, it will move from negative to positive. Does it make sense? Okay. So try to picture that as, oh yeah, electrons are obviously moving from negative to positive. That's all everything they're talking about in here. Okay. 1.2. So you're now given that electric field strength that is 5 times 10 to the power minus 6 newtons per coulomb. Okay, same electrons moving in the field. So we're sharing the same data from the question 1.1 that charge of electron is minus 1.602 times 10 to the power minus 19. Mass of electron is 9.109 times 10 to the power 31. So same method, F equals to QE. That is simply minus 1.602 times 10 to the power minus 19. That times that 5 times 10 to the power minus 6. Or what you get?
8.79.
8 point
10 to the
10 to the 10 to the power 5. Yeah, good.
Force.
Yeah.
Minus 8.01 times 10 to the minus 25.
10 to the power minus
25.
25. Yeah, more likely. Newtons. Okay, that means that this is same as M, E, and A. So the acceleration must be F on M. That is minus 8.01 times 10 to the power minus 25 divided by mass given. That is 9.109 times 10 to the power minus 31. So your value seems right to me, 8.01. Yep, so you get negative 8.79 times 10 to the power 5 meters per second. Again, this means negative simply means direction, so it's moving that 8.79 times 10 to the power 5 meters per second squared to from the negative to positive plate or the terminal. But question simply asks you the magnitude. You don't really need to worry about the direction in here, in this case. Okay, straightforward, easy calculations. Now let's find the electric field strength. Again, this is a kind of summary of what I explained in the first half of today's class. The electric potential energy voltage is defined as, please highlight that, as the work required per unit charge to move a positive point charge from infinity to place in electric field. It's really confusing. Simply remember this. Voltage equals to delta U on Q. It simply indicates that the voltage is therefore directly proportional to that, the kinetic or the potential energy. So it means that greater the voltage means greater the potential energy stored inside of the charged particles. Therefore, it can be converted into the kinetic energy. Okay, so the kinetic energy, the third point, please. The kinetic energy could be found using the standard formula, EK equals to half mv squared, but it is simpler to equate the energy gain to the energy required to move electrons initially. So what that means is this. The work done on here, the gaining kinetic energy is, this column is the work done can be calculated by Q times the V, which means gives you QV here like that. As, you can write it as this. Voltage equals to delta U on Q. That is work done on Q as well too. Or you can just same as delta K on Q2. So in electric field, this force is given by F equals to QE, okay? So which means the W, so I want you to remember what I mean by that. The work done is found by force times the displacement. And this is now known to be Q and V. Does it make sense? Okay. The work done is how we found it. So if you push something in a certain direction, lifting something, as you move in a certain direction, you are able to measure how much work you've done. Okay. The further distance you moved, the greater work done you've done. So that means that we can get the work done is equals to expression, the charge of Q. That is equals to Q. F equals Q times E times T. That's giving Q times V. Where we learned that F is equals to Q and E from the previous from in the charge particle in the electric field. What we can do, we can cancel out the Q. Okay, get the E. Therefore, E would be now same as V on D, where the V is known to be a voltage. That's a distance of the electric field. Simply, if this is two connected with a certain voltage with a distance of, say, 10 centimeters, for example, 10 and saying this is connected to 100 volts, like this, E, the electric field strength can be calculated by V on D, that is 100 divided by 10 centimeters, converted into the meter as 0.1, gives you 1,000 electric field strength. Now, the units of the field strength it can be calculated by, it's either be volts per meter or newtons per coulomb. That is the standard unit for the electric field strength. So it's either be volts per meter, as we have given the volts and the meter, or 1,000 newtons per coulomb like this. Yes. D is the work done. Same, like D and Z. Distance or displacement, we take that as the same in here, because it's moving into one direction. In this case, we are specifically using the D because we are actually using the distance between the one plate and another, which is the same as, we can take that as D is the same as this distance of the plate, same as the displacement. So you may think like I cannot skip that. Work done is equals to F times S times cos theta. This is in this case the same as F times T. Because direction would be always a perpendicular, so you're making the sine theta. So we just using that for this case. Okay. So using this, let's see how we can apply the rules. 1.3, please. What is the strength of the electric fields between two plates apart connected to a 100 volts DC supply? So the way we can do that, we're using the same. So you're given that voltage given as 100 volts. All right, the distance is given between two plates given as 5 centimeters. Make sure you convert it into the meter form, that is 5.0 times 10 to the power minus 2. Or simply say 0.05 meter here like that. Therefore, E field strength using V on D, that is 100 volts divided by 0.05, giving you 100 divided by 0.05. 2,000 volts per meter, or the newtons per coulomb. Okay, now 1.4. An electron is accelerated from one plate to another. The voltage drop between the plate is 100 volts, using that Q is equals to 1.602 times 10 to the minus 19, and that's mass of the electron too. How much energy does the electron gain as it moves from the negative plate to the positive plate? Okay, I would like to think about question A and B for about 30 seconds. We're going to go through the answers together now. After that, doesn't really use the E field. All right, so we're given the electrons moving. So let's think about the situation here. We have plate. Assume that we have a negatively charged plate. Is electrons moving from negative to the positive terminal or plate? So moving upwards like this. Okay. So initially it was like 0 in terms of the velocity. It was moving. Now it's getting some acceleration due to the electric field. So let's find it out how much of the energy it will now have. So what we're given here is So the voltage is given as 100 volts. This is amount of the voltage inserted or inserted into that charged particle of the electron. Hope you remember that. And voltage equals to the work done on Q, or also known as delta U on Q here like this. Same as, I just simply use delta K on Q's from now on. Okay, means that amount of the potential energy, which is same amount of kinetic energy, can be found by Q times the V. That is 100 times that charge of the electrons, 1.602 times 10 to the power minus 19 times 100. That gives you 1.602 times 10 to the power minus 17 joules. Okay, now, for the energies, except the gravitational potential energy, there is no negative energy. We can't have a negative energy. So we only take the magnitude of the energy. So this is the answer for question A. Make sense? Okay. Now, B. Then, how fast will the electrons be traveling when it hits the positive plate if it left the negative plate with the zero velocity? Yeah. Because we're talking about the energy. Can we? This is something like I emphasized in the two. That was only exception we make the negative energy. We do not for the rest of that. Yeah, because we can't really have the negative energy. I mean, yeah, negative kinetic energy doesn't make sense. Okay, because energy doesn't have a direction. Except that. Module 5, I know that. This is why I kind of emphasize, guys, this is something that's very confusing new, because I'm violating something I explained, but just only take the only exception. Except that, yes, this is it. What about question B? What is the question B about? This is about the conservation of the energy. That all the energy, potential energy, will now be converted into the kinetic energy. Which means, I gave you the clue. Hey, we have potential energy difference is this. Then, kinetic energy must be that too. So this must be changing kinetic energy. And it's given that K final minus K initial 2. If you like to do it, that's fine. Now, the question is specifically giving you that the electron was initially 0 in velocity. So can we take that as Ki is simply be 0? Initially wasn't moving. So that's basically same as half mv squared, which is what? Same as 1.602 times 10 to the power minus 17. Therefore, the velocity can be found by 2 times 1.602 times 10 to the power minus 17 divided by mass of the electron. That's 9.109 times 10 to the power minus 31 and square root of that. Then you'd get 5.93 times 10 to the power 6 meter per second. This is how fast the electrons are moving inside of that field at the end of the positive, when it's hitting the positive terminal. Again, using some module 5, module 1, 2, mechanic contents in module 6. So it's not a big surprise that you see a kind of question related to this a lot. Make sense? Okay. Now, could you try like 1.5 then, please? Okay, 1.5. A student sets up a parallel plate arrangement so that one plate is at the potential of the 12 volts and the other plate is positioned 0.5 meters away. Calculate the work done to move a proton a distance of 10 centimeters towards to the negative plate. Okay, please highlight that. Which means your proton is not started from the top of the plate. It's actually near at the negatively charged plate, which is around in here, the 10 centimeters, so 0.1 meter. Just convert this straight away. So read the question very carefully to understand. And I want you to think about what makes the difference here. Obviously, when we're dropping some positive charge of proton from the top, going downwards there, it will gain much greater amount of the energy. Same as I'm dropping a pen from this height to this height. Does it make sense? Okay. So you need to calculate that. What is the work done? Amount of the energy gained or lost by this charged particle. So to do so, you need to actually calculate some of the values that you're given. First of all, the voltage of that is given at 12.0 volts. Distance of the electric field is given 0.5 meter. From here, you can find the electric field strength, that is E equals to V on D, that's a 12.0 divided by 0.5. This gives you 24 newtons per coulomb, or you can also say volts per meter, the same thing, okay? This is amount of the electric field strength. Remember that, this is the strength of the electric field. This is how much that's pulling or pushing that protons inside. So what we have to concern here is, okay, then we can find the force carried by the uniform force carried by the charged particle, which is called QE. The charge of the proton is a proton, yeah? I hope you remember that charge of proton is the same as the charge of the electron with just the opposite charge. So 1.602 times 10 to the power minus 19. I gave you like 14 before, it's actually minus 19, okay? That's a charge of proton times that, the 24, the electric field strength. So 1.602 times 10 to the power minus 19, that times that to 24, you'd get 3.8448 times 10 to the power minus 18 newtons. So that is amount of force carried by that proton inside of that field. And one thing that you should not confuse, it doesn't really matter where the proton is, it will always get the same amount of force. Just like you, if you're going on the top or the bottom of the mountains, you always get the same weight force. Okay, but we can find the work done differently here. By the work done, because work done is calculated by F times the S or F times the D, doesn't really matter. Cos theta, where the theta is the direction, the angle made by the direction of the movements to the force. In this case, is 0. I keep saying cos theta, yeah, cos theta here. So it means if it moves to a certain direction, the direction of force and direction of movement, here like this, okay, it will make a 0. So gives you what? Work done is equals to simply F times the S. What we got? We got the force 3.8448 times 10 to the power minus 18. That times that, not the distance of the plate, it's actually the position of the positively charged particle, which is a proton. That's 0.1 only. This gives you then work done 3.8448. Oh, let's make it into some sig figs. We have 3 and 2, so making it into 2 sig figs. 3.8 times 10 to the power minus 19. 19 joules. This is amount of work done by the proton inside of the in this electric field. And the question is asking you, identify what does the work and what the work is done on. So what does the work? The electric field does work on a proton. It makes the proton to move. It makes the proton to work. This is why electric field does work. We can just clarify that. And what work is done on? The work is done by a proton. So it is the electric field that are pushing the proton to move, proton to work. Therefore, the proton is done some work. Make sense? Okay. Think about the subject, like which is doing the work and which is making you do some work. It's like me. I'm making you do work. You're the one doing the work. Yep. So if that helps you to understand, I'm making you do your homework. I'm the one making you do the work, and you're the one doing your work. So in here, electric field is something that making the proton to the work. Okay, like a teacher and student relationship. If that helps you to understand, and proton is the one that moved, which has done some work. Pardon? Because plates without the voltage is just a piece of metal. It's the same as like the gravity. The planet without the gravity, it's just a huge mass. Because we have a force, we have a field, we have a something for. Again, field means for the regional forces. Since we have a forces that making something to move, it started doing some work. Same as you're lifting something in the moon space where there is no gravity. You're not doing any work.
Why is that done by a proton, not by
The work is done. Work is done by. Okay, by. Hang on, it's starting confused. This does work. Okay, it should be proton does. Maybe you're right. Okay, let's say a proton does work. Let's write it right here. A proton does work by due to the electric field. So it is the electric field making the proton to do the work. Okay, sounds better? Good. All right, as I kind of give you some ideas about the gravitational and the electric field, the similarities, yes, you may get a question that is the projectile motion in module 6, even though this is module 6, which means you really need to understand the initial, the horizontal and the vertical component of the projectile motion that you learned in module 5, because we can do the same thing. But one thing, the main difference between electric field and magnetic gravitational field is we ignore the force due to gravity in electric field. The reason is very simple. The charges having mass of we don't have a mass, 10 to the power minus 27. This is kind of negligible mass. We can't weigh that electrons or protons or the helium nucleus on the scales. So something that you have to understand that we do not really concern about the gravitational field or the due to the or the force due to the gravity, unless you have a clusters of the protons or the electrons. So what I like to do is give actually let's do the 1.6 A, B, C, D. There's 4 questions here. Try now. I'll give you about 5 minutes to try question A and B now, please. Because that's something that we've done pretty much before. Earth means it's not charged. Well, it simply means it's going to be opposite charge of something else. So it simply means we have a positive and negative plate. Okay, two parallel plates are separated by 1 centimeter. One plate is earth and other has the potential of the 5 kilovolt, which simply means that it's now connected to positive and producing positive and negative plates. Okay, and with the certain distance of the one separation of 1 centimeters. A, determine the final speed of the single electron when accelerating from rest across this potential difference here. So you have to understand the point as the electron from that negative charge plate is moving across to the positive plate. Does it make sense to all? So voltage, in this case, I hope you remember that voltage is known as the change in kinetic energy divided by the Q, or change in kinetic energy divided by Q, like this. Okay, this is the same as work done on the Q later on. All right, so what we're given here is we're given the voltage, that's a delta K, would be same as Q times the V. Charge of the electrons given as 1.602 times 10 to the power minus 19. The voltage in this case is given as 5 kilovolt, so which means 5 times 10 to the power 3. The kilo means 10 to the power 3. Then you would get your answer as 1.602 times 10 to the power minus 19, that times 5 times 10 to the power 3. You're to get 8.01 times 10 to the power minus 16 joules. I'm sorry, the joules. Okay, this is same as what? Half mv squared, which is the velocity. Define the velocity of the electron. So v is simply 8.01 times 10 to the power minus 16 times 2 divided by mass of the electron, which is 9.109 times 10 to the power 31, and square root of that. So that times 2 divided by 9.109 and 10 to the power 31, square root of those, you get 4.19, so 20 times, given that we have a 2 sig figs, so 4.2 times 10 to the power of the 7 meter per second. Okay, that is the speed of the electron inside of it at the end when you reach to the positive plate. B, calculate the acceleration of the electron in this case. So you have to use the concept of mechanics quite a lot to understand and to solve the questions like this. I hope you remember that. The work done is same as change in K. Okay? The work done is always same as the change in kinetic energy, which means this is same as F times the distance it moved, F times the S times cos theta. We just take that as cos theta to be 1 because it's moving in the same direction of the field. So can we think this is same as MA times the S, where the force is equal to the MA? All right, then A would it be, move everything to the other side, delta K divided by M times the S, where the S is the distance it moved by the electron. In this case, delta K, we found that on the question A, that's 8.01 times 10 to the power minus 16 divided by mass of the electron is 9.109 times 10 to the power minus 31. That times that distance it moved from is only beyond 1 centimeter. You make sure you convert it into the meter, which is 0.01, like this. Then 9.109 times 10 to the power, 10 to the power of the minus 31, and 0.01. You should get 8.79 or 8.8 times 10 to the power of 16 meter per second squared. This is the acceleration inside of the field. Yes? You can get the same method too. I mean, you can use the u to be 0 and v to be that. So you can find it using the motion equations. You can do that too. There are various methods. There's one method using this work done. Second method, you can use motion equations. Yeah, you can. We have a velocity. What's the initial velocity? 0. Okay, what's the distance? 1 centimeters. Can we use S equals to ut plus half a, can we use the v square equals to u square plus 2as to find the a2? You can either use that, you can use that, or you can use F equals to QE. Okay, so there is a various method you can use. Did you get the same answer? Yeah, you must get the same answer anyways. Okay, now, what about question C? Now, assume the initial velocity of the electron was 5 times 10 to the power 7 meters per second, traveling horizontally as it enters halfway between the plates. How long does it take for the electrons to hit the positive plate? So I would like you to draw a diagram before you actually conduct the question here, guys, okay? I want you to draw a copy of this diagram here. To understand the question easily, I just put the positive at the bottom. Doesn't really matter for this, okay? So it gives you that a plate look like this, okay? Now, the plate separation was known to be, D was 1.0 centimeters. Can you draw the possible trajectory or pathway of the electron in your diagram? Give you about 10 seconds. Read the question very carefully. This is something that we love to use in school exam trials and the HSC event too. Okay, what you need to realize that is you have to highlight that it horizontally enters halfway between the plates. horizontally halfway, which means electron is going into the field halfway, which is 0.5 centimeters. Okay, now as it goes into the field, what do you expect? There is always simply remember that opposite attracts. That electron will now kind of move horizontally and it's kind of moving towards to that positively charged plate. We can do the same thing on the other diagram here. It will move upwards too, but this is actually better to understand the situation. Does it make sense? Okay. Now it goes downward here like that. Okay. What is this? This is a projectile motion again. But without using the A that minus 9.8, we're given we found that 8.8 times 10 to the power of 16 meters per second squared. Okay, now let's consider about the direction here, the direction of the acceleration. The acceleration applied on the electron, or what do you think? What about what would be the direction of the acceleration in that field for the electron? Downwards. It moves downwards because, again, opposite attracts. Simple as that. So you got to think about this is downwards. So I got to put the negative here again too. If you use the upward direction there, you can use a positive. But just making the I try to match that to the something projectile motion question we've done before. So you're given the acceleration, which is minus 8.8 times 10 to the power of 60 meters per second squared from question B. Okay, now what else do we have? We're given the initial velocity is given as 5.0 times 10 to the power of 7 meter per second. Now remember that this is this velocity, 5.0. This velocity going this direction. Isn't this same as the ux, the initial horizontal velocity? Now, what we learned about the projectile motion is in the projectile motions, in the horizontal components, ux is same as vx, as there's no horizontal acceleration applied. So can I just simply say the A we're given here is same as a y value then? Because it's only applied vertically. Does it make sense? Okay. Steph, what would be then uy? Zero. This is same as what? We're dropping something from the certain height. For the table, you've dropped it. Okay? And the question is asking you to find what? How long does it take? To find the time it takes, we use the vertical velocities, vertical components to find the time it takes. What do we know about then this one? All right, what about SY? Which is minus 0.005 meter. Good. We're given that. Why is it negative? Because moving from the top to bottom. Okay. All right. This is what? SY is therefore equals to UYT plus half AYT squared. That UY is 0. Half AY, we got the AY value. Therefore, minus 0.005 is equals to half times AY value minus 8.8 times 10 to the power of 16 times that t squared. Therefore, t is simply just solving for that 0.005 times 2 divided by 8.8 times 16 and square root of that. You're to get this 2.13. 2. Making into the how many sig figs? 2 sig figs? 2.1. 10 to the power minus 10 seconds in 2 sig figs. This is the final answer. Again, once you get the essence of the projectile motion, this is kind of doable question. It's simply you just need to visualize it. Okay. One thing that you have to remember is that acceleration is no longer be minus 9.8. We do not care about 9.8 because it's too small. What about D? Assuming the same condition as for part C, calculate the final horizontal displacement of the electron. How do we find that? We use this, the range Sx is equals to Ux times the T. That is, given that Ux, we're given 5.0 times 10 to the power of 7. That times the time taken, 2.1 times 10 to the power minus 10. So times 5 times 10 to the power minus 7, 10 to the power 7. You're to get 0.0106. That's same as 0.011 meter is the final answer. So even though it moves really fast speed, the electron shoots it in the fast speed, because the time it takes to hitting the plate is significantly small. It only moves that, what is that, like 11 centimeters? Only that. Okay, this is the combination of the module 5 and 6 together. Yes, it's more like a mechanic question in module 5, module 1 and 2 questions rather than module like electricity itself. You really need to understand the electricity as the mechanics. Okay, energies, forces, acceleration, final velocity, projectile motions. Okay, any questions up to here? This is the first half of the chapter 1. Okay, let's have a short break, and then we're going to move on to the next part. We actually do some questions related to that, but. Okay, have a break. Coming back in 5 minutes. Okay, page 16, and you'll try yourself question. Give you about 7 minutes. Okay, try question 1. Just what ABC now, please.